In this video tutorial, I will discuss one of the important organic molecular rearrangement known as benzilic acid rearrangement. One, two diketones having no alpha hydrogens react with a strong base such as hydroxide ion to give an alpha hydroxy acid. This rearrangement is called benzilic acid rearrangement. The best known example for this rearrangement, benzilic acid rearrangement, is the conversion or rearrangement of benzil, a 1,2 diketone, having benzene ring attached to carbonyl group to benzilic acid. Such a example is often named as Benzil-Benzilic acid rearrangement. The driving force for this reaction lies in the removal of product by ionization of carbonyl group. Both the carbonyl group gets ionized with the shifting of benzene ring from one carbon atom to the adjacent carbon atom, or from one carbonyl group to the adjacent carbonyl group, takes place in benzilic acid rearrangement. See, it is a 1,2 diketone which reacts with a strong base hydroxide ion, forming alpha hydroxy acid. Here the R and R1 may be aromatic group or group without any alpha hydrogen on these groups. There is a condition for benzilic acid rearrangement. If we use alkyl group having alpha hydrogen, alkyl groups having alpha hydrogens, then the reaction will compete with aldol condensations, may form aldol instead of alpha hydroxy acid or benzilic acid. Here it is benzilic acid. And hence, usually for benzilic acid rearrangement, we will not use aliphatic diketones, 1,2 diketones with alpha hydrogens. Then see the mechanism. Here, first of all, carbonyl group ionizes and this carbon becomes positively charged or electron deficient, and oxygen becomes negatively charged. Then hydroxide ion attacks the electron deficient carbon to form this anion. Then in the next step, the adjacent carbonyl group gets ionized, whereby this carbon becomes electron deficient, and this group, the group without alpha hydrogen, migrates from this first carbon atom to the carbonyl carbon, which becomes electron deficient, and forming this anion. Then proton transfer takes place from the carboxylic acid group to the next oxygen atom of this carbon, forming hydroxy carboxylate anion. Here carboxylate anion will be the product. Thereby, benzilic acid rearrangement is often known as an anisotropic rearrangement. Anisotropic rearrangement, because benzilic acid obtained as an anion. Okay, it is benzil-benzilic acid rearrangement. Here benzil, a 1,2 diketone, directly attached to phenyl ring on both the carbonyl group. It is known as benzil. Benzil having no alpha hydrogen atoms, and which on treating with a strong base, here it is hydroxide ions. First of all, hydroxide ion attacks this carbon, electron deficient carbon, formed by the ionization of this carbonyl group, forming this anion. Then the next carbonyl group gets ionized. This carbon becomes electron deficient, whereby this phenyl group migrates from this carbon atom to this carbon atom, forming this anion, and this anion through the proton transfer from carboxylic acid group, forming a hydroxy carboxylate ion or anion of benzylic acid. Anion of benzylic acid. This benzylic acid anion, benzylic acid anion, which is obtained as the product in benzyl-benzilic acid rearrangement. Okay. See, if we use methoxide ion instead of hydroxide ion as the base, then we will get corresponding ester. Instead of getting anion, we will get this methyl ester of benzylic acid. If we use methoxide ion as the base in the benzyl-benzilic acid rearrangement, then we will get corresponding ester, methyl ester of benzylic acid. Okay. Then when the benzyl is unsymmetrical, that means here you can see it is an unsymmetrical benzyl. One of the carbonyl group is attached with the phenyl group, while the other is attached with the paramethoxy phenyl group, and so this benzyl is not symmetrical or it is unsymmetrical. Then the hydroxide ion attacks those carbonyl group which is attached with the less electron releasing group. In this case, if we compare the phenyl groups, this phenyl group compared to methoxy phenyl group is less electron releasing, whereby this carbon atom is more electron deficient than this carbonyl carbon, because this aryl group having no electron releasing group, the hydroxide ion attack this electron deficient carbon instead of this electron deficient carbon, because this carbon is more electron deficient because there is no electron releasing group on the phenyl group. So hydroxy group first attacks this carbonyl group to form this anion. From this anion, where the phenyl group is attached to this carbon atom, migrates to the next carbonyl group after the ionization of this carbonyl group, forming this anion. Then through the migration of proton from the carboxylic acid group to this anion, we will get hydroxy carboxylate ion of the benzylic acid. It is paramethoxy benzylic acid anion. Paramethoxy benzylic acid anion. It is obtained when the benzyl is unsymmetrical, with one of the phenyl group is attached with a paramethoxy group, a more electron releasing group. Okay, as I have mentioned, aliphatic diketones with alpha hydrogens like this diketon, you can see, which having alpha hydrogens on both sides of the carbonyl groups, which having alpha hydrogens, then do not give such rearrangement, benzylic acid rearrangement, as it is susceptible to aldol condensation. But alicyclic alpha diketones give benzylic acid type rearrangement, and which is a method of choice for ring contraction. Here, ring contraction takes place if we use alicyclic diketones having no alpha hydrogens. Even though alpha hydrogens are there in alicyclic alpha diketones, it gives benzylic acid type rearrangement with ring contraction. You can see in this case, it is an alicyclic diketones having alpha hydrogens, and so it is alicyclic alpha diketones. Upon rearrangement with a strong base like sodium hydroxide, As in the benzylic acid rearrangement, this hydroxy group attacks this electron deficient carbon atom, forming this anion. Then alkyl shift takes place from this position to this electron deficient carbon atom takes place, similar to benzylic acid rearrangement, forming this anion. Here you can see ring contraction takes place, and with the proton transfer from carboxylic acid group to this anion, we'll get hydroxy carboxylate anion, hydroxy carboxylate anion of this compound. And it is a benzylic acid type rearrangement. If we use, if we use alicyclic alpha diketones or alicyclic diketones having alpha hydrogens, it gives benzylic acid type rearrangement. Okay, it is a typical example for benzylic acid type rearrangement given by alicyclic alpha diketones. Another example of an alicyclic diketone, which upon rearrangement with strong base sodium hydroxide, benzylic acid type rearrangement takes place to form this hydroxy carboxylic acid, anion of hydroxy carboxylic acid. The mechanism of this reaction is like this. First of all, the base attacks one of the carbonyl group because it is symmetrical. One of the carbonyl group is attacked by this strong base hydroxide ion, forming this anion. Then migration of this alkyl group to this carbon atom takes place, as in the benzylic acid rearrangement, forming this anion. Then proton transfer, simple proton transfer takes place to form this hydroxy acid, anion of hydroxy acid. You can see ring contraction. Here it is 6-membered ring, but in the product you can see the 6-membered ring gets converted into a 5-membered ring. A ring contraction reaction takes place with this benzylic acid type of rearrangement taking place in alicyclic alpha diketone. See this example. A benzilic acid type rearrangement takes place in this case also. Here it is a 1,2 diketone having no alpha hydrogens. These are furan molecule having no alpha hydrogens. Upon treating with a strong base like sodium hydroxide, benzylic acid type rearrangement takes place to form alpha hydroxy acid. See the mechanism of this rearrangement. As in the previous case, hydroxy group attacks this electron deficient carbon atom. After the ionization of this carbonyl group, this carbon atom becomes electron deficient. So the base attacks the electron deficient carbon atom, a nucleophilic attack of OH group, forming this anion. Then, as in the previous case, this furanyl group migrates from this carbon atom to this carbonyl carbon atom. After the ionization of this carbonyl group, this carbon atom becomes electron deficient or positively charged, whereby the furanyl group migrates from this carbon atom to this carbon atom, whereby this anion is formed. As in the previous case, proton transfer takes place from this carboxylic acid group to this anion takes place, forming this acid, hydroxy acid, with the protonation in presence of acid. We'll get alpha hydroxy acid. It is also an example of benzilic acid type rearrangement. It is the last example of benzylic acid rearrangement in this video. It is diketones, alicyclic diketones. Upon treating with a strong base, potassium hydroxide, in presence of methanol, and then hydrolysis, we will get this hydroxy acid, alpha hydroxy acid. It is a benzylic acid type rearrangement. You can see the mechanism that is similar to the mechanism as we discussed earlier. Then first of all, OH group attacks this carbon atom, whereby this anion is formed. Then you can see the alkyl shift from here to this carbon atom, whereby the ring contraction takes place with the formation of this anion, and this anion gets hydrolyzed in presence of water. Thereby we will get alpha hydroxy acid. This is also an example of benzyl-benzilic acid type rearrangement takes place in alicyclic diketone, which usually converted into, or a ring contraction takes place in alicyclic diketone. Here you can see this 6-membered ring becomes 5-membered ring in this rearrangement. Okay, these are the some important examples of benzylic acid rearrangement and their mechanism. Here I conclude this video. Thank you for watching. Thank you.